I'm Isabel Leon, and in our group we also have Noah and Ileani, and today we'll be presenting MOFs, or metal organic frameworks. Okay, so what is a metal organic framework? Commonly referred to as MOFs, metal organic frameworks are a unique category of coordination polymers. What is a coordination polymer? A coordination polymer is an inorganic polymer structure containing a metal cation center linked by ligands, and specifically for MOFs, organic ligands are used. I like to think of that metal ligand compound almost as a mer in simple polymers, and then we extend those out as repeat units, either in 1, 2, or 3 dimensions. So in the photo, you can see the metal cation centers in red, linked via the blue ligands extending in 1, 2, or 3 dimensions. Those three-dimensional coordination networks at the bottom are really nice but simplified examples of the structure of a MOF. The history of MOFs. Omar Yagi from the University of California, Berkeley was the pioneer of MOFs. In 1999, he discovered a new material called MOF 5. MOF 5 has 3 times the internal surface area of the most porous zeolite. Zeolite, discovered in 1756, held the record for the most porous material until Yagi published his research. 2 grams of MOF 5 has a surface area of 5,000 square meters, and then just as a reference, a football field is 5,300 square meters. Since then, over 20,000 MOFs have been created and categorized. However, MOFs are just now beginning to have a large appearance in research. Why MOFs? MOFs have pore structures, high surface areas, and tunable pore size and functionality. Since their discovery, MOFs have been used as hosts for a range of guest molecules in applications such as drug delivery and gas storage. MOFs in medicine. Because of their high porosity and the possibility to tune structure and composition, applications of MOFs in biomedicine include drug encapsulation, drug delivery, imaging, and chemical sensing. In terms of drug encapsulation, which is what our research articles mainly focus on, MOFs are used as matrices to load a specific drug. For this specific application, MOFs are kind of a game changer because of their highly porous structures. MOFs have extremely high drug loading volumes. Okay, this is our first research paper. It's taken from the ACS Applied Materials and Interfaces Journal. In this study, researchers develop a stimulus-responsive MOF coating, and it releases anti-biofilm compounds to inhibit biofilm formation on surfaces. Before we dive into the research, I just want to review what biofilms are. So, free-living bacteria likes to adhere to surfaces and form biofilms. Biofilms are structured communities of bacterial cells enclosed in that gel-like matrix of EPS, like slime. Biofilms provide protection to bacteria against the host's immune system, as well as provides a favorable environment for further bacterial growth, which results in infection. The primary focus of the research paper was to prevent that initial biofilm formation of bacteria because they wanted to keep the bacteria in that free-flowing state. If bacteria stays in that free-flowing state, it doesn't have the protection against the immune response, so the bacteria can easily be phagocytosed by the immune system. And then biofilms lead to infection associated with surgical implants, thus their formation would like to be avoided. In order to prevent biofilm formation, different concepts have been explored. So anti-adhesive polymer coatings, such as polyethylene glycol on the surface. That's what our image is to the right. Also, antibacterial coatings were tried. Another solution uses materials with antibacterial properties. However, because we are looking at in vivo applications, leachables and toxicity is a concern. In the research, a MOF coating is investigated as a smart host matrix for the triggered release of anti-biofilm compounds. Okay, so why the triggered release of anti-biofilm compounds? So triggered release will decrease the appearance of antimicrobial agents in the environment because of bacteria's ability to build resistance. By decreasing the number of antimicrobial compounds it is exposed to, the pressure for the bacteria to build resistance is also decreased. Moreover, by triggering the release, the coating's lifetime can be prolonged because it won't be immediately released and used all at once. To lower the release of antimicrobial agents in the environment, a specific trigger is needed to initiate the anti-biofilm compound release, but only when biofilm formation is threatening. Siderophores are a specific type of molecule excreted by biofilms, and their presence is the perfect trigger. Siderophores are small, high-affinity iron chelating compounds. They enable bacteria to attach to surfaces and make iron 3 available for the bacteria's internal iron metabolism. Because of Siderophore's high affinity for iron 3, an iron 3-based MOF was chosen for the experiment. In the research, iron chelators are used to mimic the iron chelating function of siderophores. When exposed to the chelators, the MOF's host matrix is partially degraded, which results in the release of the antibiofilm compound. The MOF coating, so in the research, MIL-A8B-FE is investigated as the matrix for the triggered release of the antibiofilm compound. The pores were then loaded with that compound, IMI, and it specifically has that biofilm inhibiting effect, and then the product structure and configuration were confirmed using PXRD and SEM. Okay, some results that I think are worth mentioning. To the left, we have a chart that analyzes the degradation of the moth with repeated exposure to that chelator. And then it shows the difference between spontaneous versus that triggered degradation. So during the exposure to just water, the amount of moth that spontaneously degraded is super low. And then once it's exposed to that chelator, you can see that it degrades. So that just shows that the coating would have a long lifetime, and then it does have that triggered gradual release. And then to the right in the chart, the biofilm growth on the MOF's coating with different masses deposited on a petri dish is compared to a reference coating, and then the reference coating is the MOF but without the loaded antibiofilm compound. So inhibition of biofilm growth is visible for all the coatings. However, the biofilm inhibition increases when we increase the mass of the coating, and then finally the biofilm was completely inhibited at that 35 milligram coating. So in this study, the researchers developed a stimulus-responsive MOF coating that releases an anti-biofilm compound to inhibit biofilm formation on surfaces. The MOF coating is non-toxic and bioinert, and then for future applications, the concept can be used to target other biofilming bacterial strains.
Hello, I'm Noah Boyer, and I'm going to talk to you today about my osteoporosis MOF research. This is a study that looked at osteoporosis treatment, drug delivery, using the MOF framework. They are being investigated as candidates for time-sensitive drug delivery of osteoporosis treatment. Alright, so what is osteoporosis? Osteoporosis is a disease which affects skeletal bone density. As you can see in the image, you have a healthy bone on the left and the osteoporosis affected bone on the right, which is much less dense and contains wide pores, which weakens the bone structure. Bone is unable to be remodeled due to deficiencies in alkaline earth metal phosphates, which help remodel bone tissue. The current pharmaceutical treatment for osteoporosis supplements these biophosphates in the body for the anti-resorptive properties. However, for these biophosphates to function correctly, adequate intake of calcium and strontium must also be supplemented. Research to develop an MOF containing both calcium and strontium ions in combination with biophosphate ligands to deliver osteoporosis treatment is currently ongoing. requires flexibility to control the dissolution properties involved in bone mineralization. This MOF framework must be time sensitive, temperature sensitive, and pH sensitive. In this study, there were 3 candidates that were synthesized and analyzed. This is the SRPAEM, which is strontium water H2PXBP, the strontium calcium PAEM, which is a similar compound containing calcium in addition to strontium water, and the hydrogen PXBB. Also, there is calcium PAEM, which does not have any strontium ions in it. So under the following conditions, the MOFs were synthesized. They were a little different in their synthesis, though they all used the autoclave to cool down and create the final compound. They were tweaked using different quantities, as you can see listed in the text. Following the synthesis, the materials were characterized using a variety of methods, including XRD, X-ray diffraction, NMR spectroscopy, as well as alizarin red-S quantitative assay for cytotoxicity testing. In addition, there was also simulated body fluid in vitro testing to determine cytotoxicity and in-body environmental conditions. All were determined to be effective at drug release and also non-cytotoxic within the human body. These cytotoxicity tests were conducted in a simulated body fluid in vitro setting. In addition, they were found to have different release rates. Strontium PAM released at the fastest rate and actually resulted in complete MOF dissolution. Strontium calcium PAM released at a moderate rate, and calcium PAM released at the slowest rate. In fact, it released at such a slow rate that there were phosphate mineral formations left behind, as seen within the image.
So continuing the study of MOFs and osteosporosis, we also study MOFs and their use to entrap bacteria that have become resistant to drug treatments. So drug-resistant bacteria are caused by the misuse of antibiotics, known as methicillin, vancomycin, and much more. So antibiotic resistance works in 4 steps. When there is a high number of bacteria, the infection is treated with antibiotics. A few of the bacteria are resistant to the antibiotics, but as the antibiotic is doing its function, is not only killing the bacteria caused by the illness, but also killing good bacteria that protects the body from infection. The resistant bacteria starts to grow, it takes over, and transfer their drug resistance to other bacteria, causing more problems that can even lead to death. So MOFs and drug-resistant bacteria is studied using zeolitic imidazolate framework, which is a MOF composed of zinc ions, and scoring was used in the study as well to be attached to ZIF-8 while keeping its photodynamic action. So the way it works is that they encapsulate scoring into ZIF-8 by a post-synthetic strategy. The insertion is expected to allow free diffusion of scoring molecules in biological media and limit the possibilities of scoring aggregation. ZIF-8 SQ are characterized by using electron microscopic techniques such as scanning electron microscope, transmission electron microscopy, and X-ray power diffraction. Following that study, they also use ZIF-8 scoring to examine its actions against methicillin-resistant Staphylococcus aureus, known as MRSA, as well as its biofilms. So the behavior is analyzed using steady-state and time-resolved spectroscopic methods, and the results are that ZIF-8 scoring showed acidic pH and red light-sensitive ROS, known as reactive oxygen species, generation due to the molecular crosstalking, and ease of diffusion of O2 through porous ZIF. Upon review, it also demonstrated that ZIF-8 scoring provided an unparalleled antimicrobial photodynamic therapy action against MRSA and led to a complete loss of adherence of bacterial films, keeping human cells unaffected, allowing a great promise of effective treatment of MRSA and other antibiotic-resistant microbes in clinical models. Some of the future work of MOFs include gas storage and separation, which takes advantage of the intrinsic pores and their volume, leading to new possibilities in sustainable energy production and use, electronic application, which demands precise control of electronic structure, and the ability to convert the metal-organic framework into glass or liquid, which shows a promise for heat storage in energy devices and for gas permeation. Some limitations of MOF include the lack of commercial availability, difficulty of synthesis, irreversible bond formations, and is limited by liquid phase density of hydrogen. The relationship between all studies showed the use of metal-organic frameworks to release drugs, two of which are concerned with combating biofilms, and in all three studies, MOFs were successful and proven to be effective. And lastly, we have our works cited page referencing our research.